Okay, so good morning, everyone. So let's get started. So today's recitation is about a general discussion of attention networks, and we would have another recitation about something more detail into what you would have for in homework 4. So today's more of a general discussion and introduction, and also we cover something starting from encoder decoder. So let's have a quick recap of what we could do using RNN so far. So the first thing you would think of is actually we have a many-to-one mapping. So from a sequence, I want to map it to single label. So consider this. You're using RNN to encode a sequence, and eventually you just make one single decision based on that sequence. And just like a task classification, you could use the RNN to do that. And also another thing we've learned, which is slightly more complex, is you learn of many-to-many mapping. So such as what you have to implement for homework 3, and you're basically doing you're mapping a utterance frame sequence to a phoneme sequence. So for this type of question, we're calling it a streaming many-to-many, because you basically have that roughly correspondence in the order of time, and from the input and the output. And you could say that basically you have for each output item, you have a rough correspondence from some segment into the input, and it comes in sequential order. So we don't actually need to have that kind of one-to-one correspondence for this input and output, the input item and the output item. I'm thinking of what? And because you could actually have CTC loss and CTC code to do this you don't have the explicit mapping, but you could actually do this using those CTC stubs. Okay, so this is what we have covered so far for the lecture. But based on just these two things we have, let's consider these tasks as examples. Okay, so for example, we might have text, we might have machine translation, we might want to translate some sense from the source language to a specific target language. But we might lose some good property of using that streaming many-to-many architecture, saying that you might have those word order correspond well from the input sentence and the output sentence. We might want to reverse those word order, or there might not be such a correspondence in sequential order. And also we might want to do image captioning. So it's not just how it would encode the image. You could still consider it as some kind of a sequential encoding, but we might not have that kind of a sequential correspondence from the output caption to the image. Okay, so you have a word that might correspond to say the upper right part of your image, but the next word might actually come out from the center part of your image. You don't have such a sequential order. And also, we might want to consider question answering. You might have document and question, and you might want to say you want to see the document, you want to see the question, you want to find the answer inside the document, and also you don't have such a sequential correspondence for you to using those previous two architecture we talked about. Okay, so today we're going to introduce a new architecture that could help you solve these tasks. So basically we have a panacea here, so it's a generative architecture. So consider what's the property of those tasks we have. We actually have an output sequence can only build after seeing the whole input sequence. Okay, so this is what we have for the task. So based on this property of the text, how we're going to solve it is actually we need to come up with a model that would help we want to generate the output itself out of the entire input sequence. That is, you cannot do something such as what you will have for a CTC RNN architecture. So we need to encode the whole input sequence first, and then we somehow inform the decoder of such a state representing the input sequence. Then we generate the output from the encoder. So here we have the very classic encoder-decoder architecture for dealing with such tasks. So thinking what makes it what makes it so different from those previous architecture we talked about, we actually have a separate part. We have an encoder and decoder, and we cannot make any prediction from the encoder alone. We need to pass the state to the decoder. So consider this. You will still have a pretty similar encoder as what you would have for those, say what you have for those many-to-one and streaming many-to-many architecture, but we're considering such a specific standalone decoder here, which is actually a conditional generator. So mathematically, we'll consider at each time step, we try to make a decision. So basically, we're predicting the current label YT based on the whole input sequence here. So it's some kind of x1 through the x capital T. And we also consider all those history of y itself. So it's y1 through yt minus 1. So this is what we have for decoder. So it's a conditional generator. It generates the label conditioned on both the entire input and those history of those output sequence. So mathematically, so how about we try to model this in deep learning? So in deep learning, we want to consider to model such a generation story. We might need to consider that the encoding, the decoder must have access to not just those decoder hidden state, because we know that we want to generate something based on the history. Basically, we'll consider RNN. So it's trivial to just do to model this y1 through yt minus 1 part. But for model the conditioned on the entire input, we might let the decoder somehow have access to the whole encoding of the input sequence. So how to encode the input sequence? So we just move back to the many-to-many architecture. We try to encode with user RNN to encode the input sequence, and you're making those decisions at each time step based on basically your expose it using those hidden states, and you're setting some training targets from those downstream tags, no matter CDC or something else, or some other sequence labeling tags. And basically, you're training these hidden states to make it maximally useful for those downstream tags using those training targets. And also in this way, we consider these hidden states might contain some useful information about both the history of the input and the output, because you're using ARN architecture. But now let's consider we just remove these downstream tags for this some kind of sequence labeling tags. And you can see that actually now those hidden states more or less would give us some information. I would store information about those input sequence using such a kind of a recurrent cell. And also, ideally, so based on the RNN assumption, ideally the last hidden state you have would contain all those past history about the whole sequence, because you're picking the last hidden state. So actually, its history is just about the whole sequence. So ideally, in a well-trained network, we could just consider using the last hidden state as some kind of a compact representation, some compact encoding of the input sequence. So we could just move from here. So let's consider just use this one to represent the input encoding, and we try to somehow pass this one to the decoder. Okay, so how could we pass this input encoding to the decoder? So one thing is actually we could we could pass it as at the first time step of the decoder. Say we okay, so we have encode input sequence, and we have a decoder here. So we have the last hidden state, and we could try to say, okay, so use this hidden state and pass it as the first input, and we have some dummy input for the later steps. And also we could say we initialize the decoder hidden state using this encoder last hidden state, and this way. But this way it might have some problem actually. In terms of how you actually building this network, you might see something that actually we just provide this input hidden state, input encoding at the very first time step. And for those future time steps, this information might more or less get forgotten. And also, you might want to let the decoder inform of these information at every time step, because basically your decoder is making a decision at every time step based on not just the history, but based on also the entire input encoder. So we might want to think of how to actually we just provide this input encoding at every time step. So let's consider this one. So it's pretty simple. So here we have a less hidden state, and we're providing this less hidden state as input to the decoder at each time step. We might have some problem here, so just consider using this one. Okay, so now what we have here is actually we try to have a fixed input encoding for the decoder, and for each item, we're using the same identical input encoding. What problem should I have? We're talking about ideally, this input encoding should contain all those information in the input sequence. But this is a very compressed, a simple assumption. Ideally, we'll have so, but in reality, it might be really hard to train such a network that make it really, really informative of all those information. And also consider this, we have short sequences, we have longer sequences, we have much longer sequences. And we're basically using, for all these sequence of different length, we're using just the less hidden states. So this might be problematic in terms of, in reality, how are these networks trained and what is the effect? We could see that more or less this would not give us some very good performance. And also another thing is actually by providing an identical input encoding at every time step, you can see that actually it's really hard for the decoder to focus, because we want to make this decision, and we can think of this as at each time step, basically the decoder will want to make decision based on different segment of the input. No matter, it could be a sequence, it could be an image, but now it's basically seeing the same thing at every time step. So it might be hard for the decoder to focus. So based on this intuition, we want to come up with some other new things to model these input encoding. So how about we just let the decoder decide what they want to focus, and let the decoder decide how we want to encode the input. So one thing we'd have here actually, let's have this kind of intuition, and let's see how we should actually build such a model or build such a computational process to satisfy this intuition. Say at each time step, we want the decoder to focus on a specific segment of the input sequence to produce the current output. Okay, so let's try to formulate this. So first thing, actually, the decoder might have different interests at a different time step. So it might want to focus on different parts, different segment of the input sequence. How should we model this? So basically that tells us that to compute such an encoding, to construct such an encoding, we should basically consider those hidden state of the decoder at each time step. And also we have second thing that actually we want to model which input segment to focus. Okay, so basically we want to consider how much for different part, how much should the decoder focus on this part. So to sort of measure, to sort of quantify this how much, we need a specific number. We need those specific focus weight to put for different parts of the input sequence. So, and also we consider we're trying to assign computer weights for different input sequence. So definitely to compute such a weight, we need to consider the hidden states of the encoder at each time step. And also the last thing is actually the most trivial thing. Actually, it should be informative of the input sequence. So we're considering building such encoding based on still those RN hidden states. Okay, so based on this thing, we could come at a general attention mechanism. So this is a general formulation. Say, at each time step, we want to construct an input encoding for the decoder, and we want to make decision. So let's consider, we want to construct a query from the decoder, say from the hidden state of the decoder at this time step I, and this query might reflect more or less what's the decoder's interest at this time step. And also, to somehow, we want to consider those encoder hidden states and want to construct the key j for each time step j inside the encoder hidden states. And this key will somehow be matched against this encoder's interest query, and to see more or less its response for this interest, specific interest. So we want to consider an attention score from this query and the key, and by representing, say, at time step I, so how much the decoder should focus on the input sequence at time step j. Okay, so and eventually we want to encode the whole input sequence. So we might have a specific representation from the input, and we're saying that we want to build this encoding out of those hidden states. So we might consider a value, Vj, for different time step j of the input sequence. So adding all these things together, the answers comes quite trivial. We just want to aggregate those Vj according to the, and weighted by the attention score. So basically you would consider such encoding of, we're summing from j through 1 to t, the maximum time step of the encoder, and also each Vj value by the attention score. So you could see that actually no matter how long the sequence is, we're giving a fixed size encoding, but this fixed size encoding is determined by the decoder hidden state. You can see that how actually Qi is playing a role here. So this comes our a network architecture prototype for considering such a attention mechanism in an encoder and decoder structure. So we try to encode each elements to input sequence, and we get a list of input encodings, input hidden states, and also we try to kick off the decoder. Say each time we're using the hidden state to generate a query, and we use this query to compare against each input's keys. Also, these keys are generated from the hidden state, input hidden states also. And we try to obtain those attention scores. And we said before, we try to aggregate the input values according to those scores. And eventually we have a compact representation of the input that is aware of the current decoder state. And we try to pass this compact representation, this context vector, to the decoder to inform the decoder of the current input, of the whole input sequence based on this current interest. So this is just what we have for a very classic encoder-decoder architecture and what the attention mechanism. So we can see actually how we should start from those tasks we want to solve, and based on those assumptions and step by step. So this is a very natural way to do this. So there might be several variations of doing such things. So based on this a very abstract formulation, so we could have different variations. Say the simplest case, the key just the hidden state, and the value just the hidden state. Also the query just the hidden state. And how to compute the attention, how to compute such a similarity, such a matching score. We're just using dot product. So we can see that actually this is very simple without any. So you can see that ideally we could achieve good performance by just using dot product. Dot product is good and it's fast. But you might think of that actually these states might more or less contain some other information. And you're simply using a dot product. And that might more or less cause those one to collapse to some sort of a pattern that is irrelevant of your those information that you should encode for the eventual task. So better way that actually we should need some transformation out of these just hidden states. So we might have bilinear attention. We try to match the Qi and Kj here using a bilinear formulation. We're using the matrix and using such thing and try to have a matching score from I to j. And you can see that actually we're using more parameters here, but this one is actually, you could consider this. We're using this one to transform the Qi first, and also doing the dot product of that transformed version. we transform Qi to Qi transpose and W, and we're doing the dot product of that transformed version against the key here. So you can see that actually we need some more transformation. So basically we're allowed to we're basically allowing some similarity calculation based on dot product, and also allow these hidden states to contain those information they want to model. Okay, so and better things actually we might have additive attention, or someone called this a concat attention. So basically also the Q and K and V and just these vectors, just the hidden state itself. But we'll consider this. We're basically passing this Q and K into a feed-forward neural network. You can see we have weight here and also activation. And also, this is a kind of attention-specific vector. So to basically want to collapse this vector to a single scalar value. So eventually, we would have this attention score, based on this MLP architecture of how we're calculating the similarity score. So this is very common, actually. So consider how you actually calculate similarity. The easiest way is to doing just the dot product. And also you might consider bilinear form. And also you might have MLP form to calculate the similarity. So basically this is based on the MLP way of calculating similarity. So we'll consider a similarity score between the query and the key. So eventually you might come to a very, very popular one, and very, it's not actually very recent, because this is what's brought up in that paper, the transformer architecture, and the attention is all you need. We have the scale dot product attention. So I want to do this. So basically, they try to model this transformation things to a. So basically, they try to do this they first map the hidden states using 3 different types of MLP, so a transformation, to map them to a key, query, and value representation. And then in that transform space, we could just do the dot product computation to more or less reflect the similarity. So we're basically doing this. We map them to a specific key, query, value representation, and we're calculating the attention scores using just the dot product of these two. And they have something new, such as they divide these dot products values by the square root of the hidden size. So they have this kind of intuition that the larger the hidden size is, the dot product value will also become larger, and actually eventually it will saturate the gradient of the softmax. So if this one's larger, actually you would have gradient close to 0 for the softmax at that point. So they try to somehow normalize this value, the scope of this dot product value. So they divide this one by the hidden state, square root of the hidden state. Okay, so basically these are very common variation you would have for implementing attention. And I think for homework 4, we'll have another recitation for that. And they'll talk about something more detailed into actually using this one for your specific text, which is a text, speech to text. And also you could consider what attention you might want to implement, and also I think you might get a good chance to have such a problem for the homework for part 1. It's not decided yet, but I think there could be an attention problem. Okay, so eventually some other kind of variation is actually heart attention. So this one's actually used somewhere. So sometimes we might want to just get down to one single input sequence. Say we want to let the decoder to focus on a less messy and a clearer representation of the input sequence. So we don't want to consider a mix-up, aggregation of these input hidden states. We just want an exact one. So in heart attention, how to achieve this one? Actually, we could use temperature in a softmax to make the distribution real peak. And so you could to approximate a 1 hot vector. And also you could do a really 1 hot using the sample, and from this categorical distribution from the attention scores. We know it's softmaxed, and also you could use reinforce or some other Gumbel parameterization trick to backprop the sampling operation. So these are things you could consider, and depend on the task itself. Sometimes it's worth trying the hard attention version. Okay, so now we should wrap up this part. So we could see that RNN-based attention is great, but it's still not. So that's why we have some new architecture coming out. So actually, one thing is actually it's very hard to parallel such a computation. We need to calculate this time step by time step, and it cannot be done. We have this time sequential dependency for the RNN states and also for the calculation of attention. You need to use the hidden state at each time step to generate a new attention vector. Also, one thing is actually for RNN, it's very difficult to consider long-range dependency. So some newer architecture might consider is transformer. So it will actually using just self-attention alone and without any other kind of linear dependency. So we're not covering this today, so you could basically follow the slides and read the paper about this thing. The transformer has become very pervasive this time. So every text people are using transformer. Okay, so next one is Lewis going to give you a code walkthrough of the implementation for a encoder-decoder architecture. Okay.
Okay, so the second part of the recitation, I'm going to have walk through of a very simple sequence-to-sequence model, which is an encoder-decoder with the attention mechanism. So this is actually, literally the simplest possible encoder-decoder. In homework 4, you probably will want to use much more tricks and any kind of techniques in this. So it will be like several times longer. Your code will be several times longer than this. So yes, we are just like showing you what it looks like. And also we basically focus on implementation in this notebook. So make sure that you have understand all the basic concepts by looking at the the recitation, maybe the next recitation and the next few lectures. So yeah, our task for the demonstration here, if you attend the recitation last week, you will probably see this one. So we are using exactly the same data and the same task, which is English spelling to pronunciation. Basically, the input is a sequence of letters, and the output is a sequence of phonemes. So we used CT2 this last time. This time we use encoder-decoders. Note that this time we have two special tokens in our output vocabulary. So we called it beginning and an ending token. So in here, we basically convert the data to the like index vectors. So we can see here, this is what we did different from the last recitation. We prepend the sequence of pronunciation with beginning and append it with an ending. And also, I think last time we used a kind of a batch first equals to true here. That's not necessary this time because that's purely for the CTC loss requirement, but it isn't there this time, so it's fine. Okay, so this part is mostly the same as the last time. So for now we can see the encoder. So basically we have three parts, like encoder, attention, and decoder for encoder decoder network. So the encoder is actually literally the easiest part. So it's not. It is actually the same as like when you use it in CTC. It's just put a sequence in and output a sequence of hidden states with the same length. So you can see here it's just a simple LSTM, but that is bidirectional. Its output here is so its output is the each time step we give you a hidden state vector. But note here that we also return the final hidden state of the LSTM because the PyTorch LSTM module returns two values, which is the output and its final state. So we put this output final state in the return as well. Why we do that? We didn't do that last time with CTC, but this time we need this final state vector to determine the initial state of the decoder. We have to do that, otherwise the decoder won't know. Like when it decodes for the first symbol, you have to know where it is. So it's very important that you put something non-trivial as the initializing vector of the decoder. Otherwise, it didn't know what to get. So the second part is attention. I think we have explained attention pretty well. So the concept here, so we are basically just like writing everything into PyTorch operations. But here we have a lot of rare things. So let's go through this implementation step by step. So we have annotated everything with shapes. The query is the decoder's query in one time step. So you can see this its shape does not contain a T. The context is the encoding of the source. So it's all the encoding of all source at once because we need to attend. At every time step of the decoder, we need to attend over all states in the decoder. And of course, it's length. So yeah. And the return will be attend the source the attention context vector at this time step. And we also return the attention vectors, which is like how much for every element in the batch, how many do we attend over every element in the source. So this is actually not used in other part of our network. We return this solely for visualization. But we not only we do visualization here, we also advise you to, when you implement your network, you also do visualize your attention matrix. Because a well-trained encoder decoder network, we have a very clear diagonal-like attention matrix. If you didn't get that, it just means that your network isn't working right. So we can see that here the first operation is called BMM. This stands for batch matrix multiplication. The shape, we use a bit of squeeze and squeeze, which is like adding a dimension with size 1 or removing a dimension with size 1. And the shape is already annotated here. So here we have an attention logics, a matrix of attention logics. The second step will be to mask out these unrelated places, because we know the context tensor does not contain valid values everywhere, because some of the input sources, the source sequence length will be smaller than t. So some of its positions will be padding, and the encoding of padding doesn't really make any sense. So we want to mask these places out. So this is how we compute a mask. So here we use unsqueeze we kind of try to utilize the broadcasting, because the one dimension will be broadcasted to all elements in the same dimension in another tensor. So in the end, we have this NT-shaped mask, where all the padding positions, or where the position is larger than the current, the length of the sequence at that line will be true. And of course, we set all these true numbers, true positions to negative infinity. We just use -1 billion here. So this makes the attention value here becomes 0. So the model wouldn't, it wouldn't attend to these vectors. So it's effectively ignored. And softmax. Take the softmax over the source length dimension, because we want for every step, every samples in the batch, the sum of attention over all source tokens to sum up to 1. So we take softmax over the source length dimension. This is the number 1 dimension in our case. And for the output, we do the BMM again. And again, you can see the shape here to get the correct, how to get the, how to unsqueeze and squeeze to get the output we want. So okay, I think it's actually pretty clear from the, the shape, our input and output here, that batch matrix BMM is actually like, it takes 2 3-dimensional tensors as input, and so it treats the first dimension as the batches. So for every element, every corresponding element in the batch, it does the matrix multiplication. And output is the batch of the result of a batch of matrix multiplications. So now let's look at the decoder. So the decoder actually takes the input, the current step of the token at the current step as an input, and the target of it is to predict the next input or the next token in this output sequence. So because it only deals with one, so it only deals with one token, one time step at a time. So there's no need to use the LSTM because LSTM is designed for like taking a whole sequence at a time. And it also has some kind of weird optimizations that we may not need here. So we just use an LSTM cell, which also works one step at a time. So the thing we did in the forward function is that we first compute the input is x. We first pass it through the LSTM. And we use the value from the LSTM to compute attention over context. So here context is just the input from the encoder. And here we get the attention context. And we concatenate it with the x. So we now have a hidden vector that's twice as large. And we finally pass it to the output linear layer to get the final result. We also return a new state. The new state here is just the hidden state of the next LSTM. The hidden state of the LSTM for the next, that will be the input of the next time step because the LSTM always takes it takes the input of the current step and the hidden state of the previous step. So we have to do this to get to pass the state to the next time step. And also return the attention. And again, yes, this is just for visualization. So for training, for training, this is just a class. After we decompose the question as we said before, like predicting the next token given the current token. So this is effectively a classification problem. And so, of course, we just use a cross-entropy loss. But this is kind of, there's many things you must take care of that's different from any ordinary classification problem. So because in a batch, you will have sequence of different length. So you will have some padding tokens in a batch. So our model, because it doesn't make sense to make your model operate on a padding node, we basically need to ignore all these padding tokens when we compute the loss. But this is not easy because you have different number of padding tokens at every step. So like you can simply set this to reduction equals mean, because then it will take the average over all tokens, including the padding ones. So you can't do that. So my approach here, actually you have many ways to do it yourself. My approach here is to set reduction to sum. And we only sum over these numbers, these positions that are not a padding. And we finally manually divide it by the number of non-padding or real tokens to get the average. So other things are not much to say. Okay, so the optimizer here. You may often just write model.parameters in the first parameter of the optimizer. But for here, because we have two models here, and we want to optimize both of them at the same time, so here we must provide a list of all the parameters that we want the optimizer to optimize. So here is the union of encoder parameters and decoder parameters. So this is also what you need to be careful of. So the main part is here. The context, we first get the context from the encoder. However, the shape here is not very ideal because PyTorch defaults to time first, batch second. So we just do a little transpose here to make it batch first, so that it's much easier to write code for the decoder. And we did assume that the context is in this shape when we write the decoder. And for the decoder part, so the second block of code here is the decoder part. So this is what actually the decoder is working on. It basically takes the tokens in the current time step as the input, and the context and the context length, which is the same as the x length because we didn't change anything here, and the state. So the state here, we can see the state is assigned to state. So basically the state here always holds the, the previous state, and it returns the next state. So here this is the active here. So y length is the a one-dimensional tensor that contains the length of all output sequences. So I plus 1 smaller than y length is that. So y plus 1 because we are predicting the next token. So next token is at index I plus 1, but I plus 1 must be in the valid range of a sequence. It can be neither I or I plus 1 should be on the place of a padding. So the condition that the current step is still active or is not, we didn't go past the end of the sequence, is I plus 1 is smaller than the length. So here active becomes a Boolean mask that we can use to filter out all this. We can use it to take only the active samples in the batch from the output and the ground truth to compute the criterion, to compute the cross-entropy loss. So note that we are using, so remember that we are using sum, a reduction sum here, which means that the loss here is the sum of losses at every tokens. So at the end, we divide the loss by the number of real tokens in the batch. And this will be our average cross-entropy loss for this epoch. For this batch. But here we actually use one batch per epoch, so yeah. So here, this is, for here we have some attentions here. We assembled all the attention vectors into attention matrix for visualization. So this is also not used for computation. And of course, in the end, we just do the normal things that we do for every neural network in PyTorch. So our data set is very slow, so this is definitely overfitting, but yeah, at least it works, right? So here, we have some visualization. So this is not required, but still, when you write your network yourself, you will want to do this because this helps you with debugging. So the code here, so yes, matplotlib is a huge mess. You should just look at documentation to find out the right way that prints the most beautiful visualization for you. For me, this just works, and yeah, let's see what it looks like. So here's just a training loss, training curve. This looks converging very well. So these are the attention matrices for each word. So the x-axis is the input, the y-axis is the output. However, we can see that it isn't working very well for here. So I'm not sure why. Maybe because our sequence is way too slow, or way too. Our sequence may be way too short, and our network is way too small, and we are like blatantly overfitting the whole data set. So I mean, like, it has too many parameters in our network. The network can just like the decoder can just like memorize all possible outputs, so it didn't need to attend to the encoder. So the so the attention here isn't looking very good. But we can still get some clues sometimes, like for this, like the first sample, C. So C, we can see the first S is aligned to S, so this is common. The second phoneme E. So you know in English you never pronounce the you don't pronounce the same single E as E. You pronounce two consecutive E's as E. So you can see it attends to two E's at the same time. So you can see this. Sometimes it makes sense, sometimes it didn't. Like the set here. So set the E, it doesn't attend to the E. So this is strange, but for S and T it does, right? So yeah, just like that. For long, if your sequence is long enough, like 10 or 20 symbols on both the source and the target side, you will see a clear diagonal line through the sentence. Because usually, I mean, no matter what language you are using, you always like having some kind of word order correspondence. So that's true for translation. In translation, actually, different languages have different word orders, so even not very good. But for our homework 4 is actually so it's also a speech recognition task. So you can imagine that the sequence of sound, the sequence of voice, and the sequence of the actual text you are saying has a very good linear correspondence. Like you are not going to say a word backward, right? So, and no one is going to spell a word backward, right? So you will see a very clear diagonal line on your attention matrix when you do the homework 4 part 2. And yes, we strongly recommend you to visualize your attention matrix. So here comes the last part, it's called decoding. This is very different from training. And unlike homework 3 part 2, we doesn't allow you, you are not allowed to use any third-party libraries to implement the decoding part. So this will become pretty complicated. Here we show one of the easiest way to do decoding. It's called greedy decoding. This means that for each time step, because we have the decoder outputs a probability distribution over all possible tokens, we pick the one with the highest probability. And this becomes our output of the current time step. And also we feed it into the decoder again as the input of the next time step. So this is a really easy way to do it. But currently, most people will use beam search. So beam search is like we try top n best tokens at a time. And we compute for all these n possibilities, we compute all the possibilities. We compute all possibilities in the next time step, and again we select n best best possible outputs in the next time step too, and do it again and again. This is actually pretty complicated, so I'm not going to demonstrate it here. But one thing that's good to know is that greedy decoding is equivalent to the beam search with beam width 1. And if your network is well trained, greedy decoding wouldn't be as good as beam search, but it wouldn't be crazily bad. Like, it probably will still like, it will probably like make your score worse by like 10%, for example. It won't be like, it won't ruin your output. It would just be slightly worse than beam search. So I will suggest you to start with this one. And then you can, after all the rest of your network works fine, you get reasonable outputs, you can switch to, like, you can then start to implement beam search. So here we have some test data. So these words all these words are not included in the training data. And yeah, we just do some standard stuff, standard data transformation stuff. So here, so ideally you should do a decoding a batch at a time because actually in a computer, GPU. So when you want to communicate, like send data from memory to GPU or from GPU to a memory, this is actually has a very large overhead. And you don't want to do it like for each sequence, you don't want to do it tens of times. So the ideal thing when using GPU, you will always want to do decoding a batch at a time. But this will also add some very non-trivial complexity to the code. So here we just demonstrate how to do it one step at a time, one sample at a time. So you don't need to worry about any of these things. So the code here is pretty much the same. Like at the decoding part, at the encoder part is the same. For the decoder, so we have a variable called input token here, which we start with the beginning token. When the decoder receives the beginning token, it knows that it needs to look for the first thing. It learns the decoder knows that it should attend to the encoder's first part. So we definitely need to like start a sequence with the starting token. So here we decode step by step in a loop. So we should like be aware of the ending terminating condition here. So of course, if you generated an ending symbol, this means that yes, the decoder decided to end here. So you shouldn't try anymore. So this is one of the stopping criteria. The other is that the length, if the length goes too long, you must also stop because it's very common that encoder-decoder model's output becomes like looping through a few words again forever. If you didn't do it, you will never end decoding a sequence. So you must set an upper limit of the length of your output, and you force it to stop after that, right? And yes, we take a step. This is the same as our training, and take the most probable output token. We append it to the sequence, which is the output of our decoding, and we use it as the input of the next time step. And in the end, after the loop ends, the sequence, this variable contains all the output tokens, and we print it out. The result is here. This is actually very bad. It doesn't make any sense. It doesn't even get it didn't even get the first consonant right. But for the vowels, let me see. So yes, all the vowels are correct actually, but it's somehow messed up with the consonants. So this is actually, you can see this is performing much worse than the CTC last time. But this is just a toy example, In real world, CTC cannot deal with non-sequential correspondence, non-monotonous, monotonic correspondence. Like if we are translating when the two languages have different word order, CTC would not do the job. Even when you are doing the the speech recognition, sometimes some words have it's not very common, but from time to time, you have to look at the pronunciation of one letter is sometimes depend on the other on another letter after it. So actually we can see examples here. So here like sit and sight. Why the I is pronounced differently is because the E at the end. If you're using so because we are now doing spelling to pronunciation, but in homophobe we are doing pronunciation to spelling. So you will not be able to CTC will not be able to capture this kind of relationship because it depends on the information that's not the vowel E or I correspond to I, but it's also related to the E after its next symbol N, next symbol T. So this is kind of non-monotonic correspondence. This CTC cannot model this one, so it will be better. It will be much better if we want to directly use encoder decoder. If we want to directly generate English, and I mean human readable real English from speech. And yes, that's all of it. Do you have any more? So yes, that's the end of the dissertation today. If you have any questions, you can just ask now.